Yeah, today's talk, Non-Markovian, reaction transport by Vincent Mendes.
Yeah.
Yeah.
All right. Thank you very much. This talk is, in fact, is a continuation of the talk that before yesterday Sergey gave. I'm going to insist again in the application of non-Markovian reaction transport process. But now I'm going to center the interest in a very important ecological problem that is known as biological invasions. Let me begin to explain you what is biological invasion. Biological invasion is a process that occurs when a new species called invader is introduced in a new territory where this species is not autochthon. And then it begins to spread, to move through the territory, through the new territory, and reproduce on this territory. So there are two important processes here that have to take into account if we want to model. That is a movement, a spread, dispersal, whatever kind of movement, plus reaction, plus reproduction of these individuals. Is a very important problem in ecology and in biodiversity. But it's not only an important problem in ecology, it's a very important problem in economy, because the economical costs that many countries have to invest to break down an invasion increases almost exponentially from the initial instant of the introduction of the invader in a new territory. There are very well-known invasions, are well documented in ecological monographs, ecological papers, but I will show you some of them. But keep in mind that an invader can be an animal, plant, or even a microorganism that invades, like for example tumor cells, that are cells that are able to invade an organ, etc., a tissue. So one of the most important in ecology, one of the most important invasions in ecology is the plant invasions. Plant invasions are estimated to invade the planet at a rate of almost 19 kilometers square per day. This is a huge area invaded per day as a mean value. Here I put here two different features of a given landscape. First, in this case, the landscape is covered by the native grass, and here is covered by the invaded grass some years before. Okay, so some years later. Sorry, it's completely different. So it is a very important biodiversity problem, but it doesn't happen at big scale. Plant invasions are very common, and we can find it in our own garden. For example, this garden had typical grass, and these new plants that appears here suddenly are invading this small territory. So invasions are almost everywhere. Another very famous invasion here in Britain is the invasion of the American gray squirrel at the early 19th century that invaded the local red squirrel. Actually, it's very difficult to find a red squirrel here in Britain, because this invader has driven this squirrel almost to extinction. And
Are the grey ones yet less useful than the red ones? Or is it no harm? is nice.
Who knows? There is a competition for resources, resistance. Who knows? Is adaptation to the environment also. And the last example is the case of zebra mussels. Zebra mussels are mussels original from the southern Russia. And actually they are invading many countries in Europe, and also they have invaded the USA from north to south along the Mississippi River, and in almost 9 years they crossed completely from north to south the USA. So it's a horrible invader, zebra mussel. Well, what ecologists think about what are the mechanisms behind these biological invasions? At individual level, if we observe what is doing each one of these individuals when they invade a territory, what they do is when they burn, they reach the adult age, and then they move randomly to find another place, another position, a new position in the territory, and in this new position they reproduce. So the new individuals that have born in this new position, when they reach again the adult age, they move to another position, and the process is again repeated again and again. So what we conclude is that the invasion process is a combination of motions and reproductions. Motions from one point to another point, and reproductions while the individual has reached a position. When the individual reaches a position, it waits at this position, begins the reproduction, and when the new individuals reach the adult age, the new movement begins again. So, our couplet processes, movement and reproduction, are not independent anymore, are couplet processes. So, this is the information we can extract from ecologists. Now, as a physicist, we ask, okay, how to model, how to describe both phenomena. Biological invasions, for us, can be regarded as a reaction transport process, but very peculiar reaction transport process. The transport process can be described simply by a random walk. But the random walk has to be in a very specific way. A random walk can be dispersal process, because it's not enough sometimes to consider that individuals move according to Brownian motion, because most of the individuals move, they have a proper locomotion system. So Brownian motion is only an approximation. We have to take big tools, mathematical tools, to deal with dispersal process in general. So for us, dispersal process means that the individuals jump, and the jumps are random variables distributed according to a PDF. But also, in the movement, we have to consider the resting phases and the times, and these times that the individual spent at a given position, we will consider that they are also random variables distributed according to a waiting time probability distribution function. Of course, besides this...
Can you consider this as time delays, kind of?
Yes, this is like a time delay. Okay. But time delay is macroscopic Macro is a macroscopic quantity. I'm talking about microscopic quantities. But out of these microscopic quantities, when you perform the macroscopic limit, many of them, in many cases, you can have time delay. Yes, but the time delay, the origin of time delay is a waiting process, right? Then, together with this, random walk, that could be what we can make use to describe transport. Now we have to add reaction. Reaction is reproduction of individuals, proliferation. And we know that this proliferation has to be taken into account during the pauses, during the resting phases, during the periods where the individual is static at a given position. And to model this, we could take into account simple classical kinetics, like for example logistic growth or whatever. Right? Let me explain you which are the most famous models that have been proposed to deal with biological invasions. The oldest model is due to Fisher. The Fisher model appears in 1937 and is a parabolic reaction diffusion equation like this one. Almost everybody knows Fisher equation. It appears in many books by mathematical biology. And Fisher equation is macroscopic, is an evolution equation that is able to describe biological invasions. But I want to draw your attention in the following thing. This equation can be described in the following way. This is the rate of the number, this is the temporal rate of the number density of individuals, and this rate is due to two contributions. One contribution is due to migration of movement, in this case diffusion, plus another contribution, this is reaction, right? So here we additively combine these two processes. But this combination is right. Why? It's the same idea that Sergei explained the other day. Behind the diffusion process, this is a macroscopic equation, there is a microscopic interpretation such that this process is Brownian motion, because the macroscopic limit of the Brownian motion is the diffusion equation. So the origin of this diffusion equation is Brownian motion. And Brownian motion is Markovian. And why is Markovian? It's Markovian because each step in the Brownian motion is independent from the previous one. So there is no memory. And since there is no memory, the process is Markovian. It's simply like that. So this is Markov process, and classical kinetics is also Markov process because can be described from a master equation, Markovian master equation, blah, 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 right? So both processes are Markovian, can be additively considered together. Well, this equation has been applied for many biological invasions. You can read the books by Murray, the book by Okubo-Levin, and many other books that deal with this problem. However, one can think, okay, Brownian motion probably is adequate for some organisms, but many of us know that is not adequate for example, cells. Imagine a bacteria that has a flagell. It has locomotion. It doesn't move according to Brownian motion. Choose a direction, then waits, run and tumble, run and tumble. This is not Markovian process. There are waiting times between successive jumps, and then this complicates everything. One of the generalizations, historic generalization, was due to Goldman and Kack, that they proposed a generalization of the diffusion process, and they obtained the telegrapher's equation. Again, telegrapher's equation is a hyperbolic partial differential equation in this case, because it appears here second derivative in time. It's a macroscopic equation, but again it has a microscopic description behind. In this case, the microscopic description is a correlated random walk. And Goldstein and Kack began describing the correlated random walk. They performed the macroscopic limit, and they obtained this equation. So behind this equation, there is also a microscopic description. But look, correlated random walk means that the steps, the successive steps that the individual perform, are no longer independent, are correlated. So there is a persistent index, there is a persistent in a direction of motion. And when you perform the macroscopic limit, this persistence appears here in this tau, right? This can be also, of course, this equation can be also obtained from phenomenological laws. I don't know if you are familiarized with this kind of telegrapher's equation, but this can be obtained if you combine a valence equation for density of particles and a constitutive equation for flux, that is Catania equation, right? But again, in Catania equation, there is a first derivative of the flux that give rise to, as a consequence, this term. So this equation, behind this equation, there is a clearly non-Markovian process. Now, the problem is, okay, we want to add here reaction. How do this? How to include reactions? It's so simple like this, to add to the right-hand side a reaction rate term, like logistic term, for example. The answer is no, because again, we are mixing non-Markovian equation, an equation with non-Markovian origin, with an equation with Markovian origin, and we can do this. So in fact, I have not written in these slides, but it is very simple to write down the proper telegrapher's equation with reaction. If F capital rho is the reaction rate, this could be logistic, whatever, general reaction rate, then the equation for the evolution of the telegrapher's equation with reaction is this one. It was derived, the first guy who derived this was Karl Hadler. So look that in this case, it's not only enough to add here the reaction rate, we also need this derivative. This prime indicates derivative with respect to rho, right? This is the reaction telegrapher's equation. This is the correct equation, right?
And the derivation is done using the microscopic level, so you start really through. Oh, it's just done by a macroscopic approach. How the derivation is done, or you have a reference for the where this thing comes from?
Yeah, from the papers by Hadler,
Okay, Adler.
yeah, Carl Hadler, or in the book that Sergei presented in our book is also, we have different derivations of this equation. This can be derived phenomenologically, for example, or also following the ideas by Kak and Goldstein and Kak, because Goldstein and Kak, so the derivation proposed by Goldstein and Kak is to write down balance equation for particles that go to the left. So microscopically, this can be interpreted as an equation that particles perform jumps with a finite speed, plus v0 minus v0 with the same probability, but the rate of jump to each direction is not the same. So there is a persistence, right? And this, what they do is to write down equations for the balance for particles that go to the right, particles that go to the left, etc., etc. And here there are switching terms. And then, as a consequence of this coupling together, if you define rho as rho plus rho s, then you get the telegrapher's equation, right? But if here you add, so this equation is Markovian, this equation is Markovian, and here we can add reaction rate. For example, 1/2 of the reaction rate are particles that go to the right, and 1/2 go to the left. Combining both equations, you get this. This is one derivation from the ideas by Goldstein and Kak. The second derivation is make use to the balance equation for this is the density and the flux of particles, and here this is equal to reproduction term, reaction term. And now consider Cattaneo equation for constitutive equation for flux. The combination of these two equations gives, again, this equation. But there is a third derivation that we present in our book that is based on the continuous and random walk, because we like very much continuous and random walk because it's a very general framework to deal with many possibilities. It has many possibilities, and you can find all these equations as particular limits. So this is a very general framework. This is why we are interested in continuous and random walk. Well, one of the problems of this is that it doesn't obey the principle of correspondence, because, for example, if we remove this part because the medium is homogeneous, in the homogeneous case, we should recover the kinetic law, but we don't recover the kinetic law. We recover the kinetic law plus this term. So we have a problem here. And this equation has oscillations, and oscillations imply that this guy can reach negative value, and this cannot be, has no physical meaning. More recently, some people have tried to derive a generalization of the Fisher equation simply by doing, the idea is very simple, is they write down this balance equation. This balance equation means that this is the difference of the densities at different times at the same position, and this difference is due to two contributions, migration and growth. Again, if they sum, they are assuming implicitly that this is both processes are Markovian. And they perform the limit, the macroscopic limit, when t capital tends to 0. Okay, when t capital tends to 0, they obtain the contribution for movement, the second derivative, but the contribution for reaction, they obtain not only the first derivative, but also second derivative. So they are considering a Taylor expansion up to second order in T capital. And so they obtain this equation. But it's not a good equation. It has many problems. We have published last year, we have published recently a paper analyzing all the problems that this equation have. For example, it doesn't reduce to the kinetic equation again in the homogeneous case. This equation introduced new equilibrium states coming from the fact that this guy can be zero. And these equilibrium states has no sense, no physical meaning. In addition, when you consider here that F is simply a linear death rate, so it's a simple death process linearly, you can solve this immediately because the equation is linear, and you observe that regardless of the initial condition, rho is negative. So, bad equation. What we propose, this is proposed in our book. We propose that the biological invasions can be described by using continuous time random walk. It's a general framework, and we can add, it's not easy to do it, but we can add to the continuous time random walk, we can consider reactions. Let me remind you what is the continuous time random walk and the big result of this theory. The big result is this equation. This is the generalized master equation. This master equation contains two important guys. This guy that I have highlighted in red. This guy and this guy. These two guys, this is the PDF for jump distances, the probability distribution function of jump distances. And this is the memory kernel. This memory kernel is related to the waiting time distribution phi in the Laplace space, right? So in fact, in principle, we have two important functions, two important PDEs. One for waiting times between jumps, and one for dispersal distances, right? The only case in which this equation is Markovian is when the waiting time distribution is an exponential distribution. In this case, in this particular case, this equation turns into the well-known Kolmogorov-Fellers equation, Markovian equation. And in this case, we can add to the right-hand side reaction term without problems, but only when phi is exponentially distributed. In the rest of cases, is not Markovian. Well, the question is how to include reaction here. Of course, it's not possible to add simply a reaction rate to the right-hand side, to this balance equation, okay? Let me introduce some notation. If this is the F capital is the rate of growth, and we separate this, we write this in this term, in this way, this R has two contributions from birth and death processes. So this is simply notation. We have two options. There is not a universal way to implement reactions together with continuous time random walk. Sergei told this exactly the other day. There is no universality, because the difference is that when the new particle is born in a given position, we have to take into account what is her waiting time. Is zero, or is the same waiting time as their parents? So in principle, we have these two possibilities. Model A is the case when the new particle has the same waiting time as their parents. In this case, I have skipped all the details of the calculations, but you can find in our book. Again, is a very similar equation that Sergei presented the other day. Of course, we have here at the right hand side the reaction rate, but we have also here these terms coupled to dispersal processes that appears because of reaction. So in general, reaction and transport process here are coupled, unless the waiting time distribution is exponential. In this case, when this is exponential, everything factors here and everything can put out of these operators. In the case of model B, when the newborn particle individual has 0 age, we have a very similar equation. It's not exactly the same, it's very similar. The difference is that here we have this R minus that implies the destruction of individuals, so the death of individuals in comparison with this one. But now the question is, one question we have to solve is what is the best equation for modeling biological invasions? For modeling biological invasions, ecologists agree that is the first one, because in most cases, the newborn individuals keep at the nest until they grow, they reach the adult age and are able to reproduce by themselves. And then, before reproduction, they go to a new positions and reproduce there at the new position with new resources, right? This is the question. So for us, the model A is more adequate for biological invasions, but for other process probably could be the model B, right? But one of the most important out of the model, what can we calculate? We have a model. What can we calculate? The invasion velocity. The invasion velocity is a measure of the rate of invasion, right? And we can calculate this invasion velocity out of our models. To this end, we will consider that the reaction rate is of logistic type. It means that we have two equilibrium states, rho equal to 0, rho equal to 1. Rho equal to 0 means that there is no population, is the region where there are no animals, nothing. And rho equal to 1 is the invaded state. So this is like a phase transition that is advancing from rho equal to 1, invading the region rho equal to 0. So rho equal to 0 is unstable, and rho equal to 1 is stable, right? Well, and here there is this factor is the intrinsic growth rate. Well, in this case, we can assume the existence of a traveling wave solution, as is pretty usual to do this traveling wave solution in reaction diffusion equations. And assuming that these traveling wave solutions begins with initial condition with compact support, and this traveling wave moves after a transient, moves at constant velocity, connecting these two states, right? Well, once we have assumed this, we can analyze, we can obtain the front velocity in such a way. Since the reaction rate we have assumed is logistic, it means that the dynamics of the front is governed by the tail of the front, by the tail. So by the case when the number of particles is low. And to situate the problem to the tail, we perform this hyperbolic scaling. And then we do epsilon tending to 0 later. We define this new field, and we propose these WKV ansatz, and you will see very soon that we end up in a couple of two Hamilton-Jacobi equations. So behind the problem of invasion velocity, there is a Hamiltonian structure. So the front position can be studied with classical mechanics. So we can propose, we can find, we can derive the corresponding Hamilton-Jacobi equation for each model, and identify the Hamiltonian, the conjugated momentum, etc. What appears here, look, is here. This is this integral transform of the dispersal kernel, and this hat indicates the integral in fact, this is the Laplace transform of the memory kernel, right? What happens is the following. Note that, for example, this integral, if this dispersal kernel, this can be measured experimentally from data. If this dispersal kernel decays faster than an exponential, then this integral will converge. This is nothing but the moment generating function of this PDF, because it's multiplied by an exponential and integrated over the whole space, right? However, in many cases happens, in many invasions happens, that this guy presents a tail that is heavy tail. So the tail it doesn't decrease as exponential, but decrease like power law distribution. And in these cases, this moment generating function doesn't exist. And this is saying that the invasion velocity is not constant. In those cases, invasion is accelerated. And this theory breaks down. Okay, is the limitation of this theory. What we observed is this couple of Hamilton-Jacobi equations relate h with p. And this relation between h and p is useful because the measure of the velocity of invasion is given by the minimum of this quotient. We can, if we express h in terms of p, we have to minimize over h. If we express p in terms of h, we minimize in terms of p. Doesn't matter. The question is that the from velocity depends on three magnitudes. Depends on the dispersal kernel and the moment generating function, its moment generating function. Depends on the waiting time distribution through the memory kernel, and depends on R. Look, these three magnitudes are here: K, phi, and R. So the velocity, I don't know exactly the exact form of the velocity, but I can ensure that it depends on these three magnitudes. Only three parameters we need to feed from experimental data to calculate the invasion velocity. Then the next question is how to do this. The dispersal kernel, phi capital, can be measured from mark recapture experiments that ecologists do. They do experiments of the distance traveled by the individuals. They collect all of data and they perform frequency histograms. And then we feed this function to this data. But the waiting time distribution and the intrinsic growth rate can be estimated from life statistics. From life statistics, once we have defined what is the period that a female is able to reproduce, we can define the following functions. The survival function is the number density of newborn females that survive to age t, and the fertility function that are the rate of offspring produced by a female at the same age t. So the product is the maternity function. In population dynamics, there is an equation called Euler's equation, is in fact an integral equation consisting of the maternity function integrated, multiplied by this exponential, and here there is the intrinsic growth rate. We have to solve numerically this equation to estimate this intrinsic growth rate. But many of these data are available and are measured by ecologists. And finally, the waiting time distribution. The waiting time distribution is the time, is the distribution for times spent from the birth of the new particle, from the birth moment to the adult age. The time spent is a random variable distributed according to this distribution function, and is computed from life statistic data in this way. But now I want to draw the attention, because this is very important. So I'm saying that, I want to keep this. Okay. I'm saying that phi is essentially the product of L and M, conveniently not normalized, right? Okay, if T is small, it means that the adult age, this is the adult age, and this is the distribution of adult ages, because it's the time spent from the birth of a female till the adult age for this female. When the adult age is small, what happens? The maternity function has to be small, right? So M, T, has to tend to 0. Phi tends to 0. But the opposite limit, when the adult age is large, is very large, happens the same. The female is very old, and then the fertility also tends to 0. So again, in this limit, F tends to 0. And what life tells us is that the females have an optimum adult age when they are able to reproduce. So what happens? That phi, in terms of T, behaves qualitatively like this. And this is not an exponential distribution. No. What this means is that all of this model is non-Markovian. So this is the importance. Okay, you can find in my second book, it's not available here. The first book is available in the library of the Institute, but this second was published 2 years ago. And in this second book, we explain how to measure this, how to apply this to movement ecology and things like that. Well, this is a detail of how to do this when invasion takes place in 2 dimensions. The only thing we have to do is properly define the moment generating function in 2 dimensions. And let me only to end up this conference, this talk, let me show you an example, simple example. There is a simple example that is the invasion of muskrats also at the early 20th century. That was these guys invaded the north of Europe in this time, and was estimated roughly that estimations say that they invaded the territory at 11 kilometers per year, and we found data about in this period about the dispersal kernel and the waiting time distribution function. We feed this and we compute numerically with model A that the rate of invasion out of our model B, our model A, sorry, is this quantity. Is not bad approximation. So to summarize my conclusions of this talk, the goal is to convince you that biological invasions are non-Markovian reaction transport process, that to model non-Markovian processes together with reaction, it needs to be done with care. Some authors insist in playing with equations without knowing the process that is behind, and this drives to wrong equations. For us, continuous and random walk is a good framework to deal with biological invasions. They have many possibilities. Our adequate model for biological invasions is model A, and that's it.
So your framework, it looks like you're dealing with a single species. Can you deal with multiple species within this framework?
Sorry?
Multiple species, competing species?
No, I have only tried with invasions, so this model is only, there is no competition between the species,
yeah,
of course.
yeah.
It's only the invasion of a species in a territory where there is nothing, only resources for living there, only resources. So there is no competition.
In 2 dimensions, will your model have undulation instability?
Instability.
Yes, instability, undulation instability, transverse instability.
Probably, but we need to have the finite environment, so a finite environment. In these cases, traveling waves propagate in an environment that is infinite, so we have no boundaries in this case.
No, I mean in 2 dimensions. You have an invasion front,
Yeah.
right? Would it stay straight or would it develop instability?
In principle, the traveling wave is a monotonically decreasing function. So, traveling wave solution, that is what we describe as the propagator, as the invasion process. So, if we plot rho versus the space, it behaves like this. So, it's a monotonic. This is monotonically in 1 dimension. No, but in 2 dimensions. In 2 dimensions, these are cycles, because we assume radially isotropy.
Well,
So.
but you assume it. But
Yeah, of course.
Your equations can they be formulated in 2 dimensions?
Yeah.
So if they are formulated in 2 dimensions, many fronts develop instability.
Yes, because
So
the curvature
they
and
propagate in an unstable.
Yeah.
They have some. So this apparently this is important for invasions, because invasion, well, of course, real invasion is in a very is an environment which is not homogeneous, but even in homogeneous environment, many fronts tend to develop in a different way.
Yes, but it depends on this.
They go.
It depends on this guy.
direction.
If you have an activator-inhibitor system, you can have this kind of instabilities. But if this is like a logistic growth, you can never have this, because this is a stable state and this is unstable state, so it dominates everything. The spirals and these kind of instabilities that you can have here. No, I know the papers that you are thinking by Eric Hagberg and these guys that developed calculated the velocity in terms of the curvature of the waves that propagates, but they need a reaction rate that has to be activator-inhibitor system.
Yeah, well,
Stability.
This is in a standard model.
Yeah.
But, it would be your model is more complicated. So it is a question really how your problem would behave in 2 dimensions.
In our case, if this reaction rate is a logistic, we expect And if we assume isotropy, we expect this. We don't expect anything else. If there are anisotropy, is probably these circles destroyed. There appear fingers. I don't know, because if are preferred directions, then the front could be broke down. I don't know. We have never tried to investigate this case.
I was actually going to ask about the reaction rate, so you sort of answered. No, because I was thinking along the same lines that you're looking more at a colonization than an invasion, and that with a sort of more funky reaction rate, you'd be able to somewhat. So in terms of the spreading speed, for example, are there things you can do in a sort of more generic way by just assuming, you know, some properties of the reaction rate function rather than just assuming a logistic? Are there things you can still do if you assume genericity in the function? I mean, if you just assume it has some basic properties.
Exactly. Much
Well,
more general than the logistics.
of course, this theory for the front propagation, this Hamilton-Jacobi, this structure holds only when this condition is fulfilled. F prime at rho equal to 0 is positive. There are many reaction rates in population biology that don't fulfill this condition. And then this theory is beautiful theory, because for us, for physicists, is based on classical mechanics, right? But for example, there is a kind of reproduction rate that is called reproduction rate with a Lie effect. A Lie effect is an effect that happens when the population density is small. When the population density is small, ecologists find that the mating between female and male is difficult, because population is, the density of individuals is small. And then they consider this in a reaction rate. In this case, for example, our theory doesn't hold, because F with rho behaves with a Lie effect, behaves like this. And in the logistic case, behave like this. So we need that the slope of the function at small densities has to be positive to apply this theory. In the bistable case, so this is bistable case. It doesn't work.
I wanted to ask you about this telegraph's equation with the reactions. So you said it can be derived from this thinking about these two species going left and right with some velocity. So when you do this derivation, this intrinsic velocity goes into D, I guess, right? It's now part of the definition of D.
Yes, the definition of D is different.
Yeah, I just wanted to clarify that. And then you said that this equation, the problem with that is that it doesn't have a uniform solution with a stable positive density. You said the density goes to negative values or something like that.
Well, a parabolic equation has problems.
So isn't this the problem that in fact the assumption here is that these animals move with this velocity and with this persistence independent of density, and in reality when the density is increasing the persistence will go down, and therefore tau will in fact be density dependent and possibly also D, and that will slow down the diffusion and also their persistence when the density is increasing, and that will in fact remove this problem from the physical system. Because I was thinking, what's the problem here? In fact, I mean, particles or animals can move persistently and reproduce and still exist in real world. What's the problem? And the problem, I guess, with this equation is that you don't have these density effects.
With this equation, with telegrapher's equation,
Yeah, and won't these density effects, if you include them, make this equation well behaved and describe very well,
yeah.
the real situation?
No, you're right. If we consider tau or d that depends on the density, is a more realistic situation. But in these cases, to study the front propagation I think, is very difficult because it includes nonlinearities and makes things more complex.
But
That-
for the front, but just for the front propagation, this equation would be fine, right? Because you said that the problems with this equation come
Yes,
when
yes,
you
yes.
deal with the uniform state and not with the front.
Yes.
Okay.
No. For front propagation, probably we could find a front propagating at a given speed.
Right.
The problem is how to calculate this speed if it is nonlinear. So we only know analytically it's possible to calculate the velocity analytically only under this condition. If you have nonlinearities, if you have more complex situations, then you cannot do this analytically. Because analytically, when this happens, since the tail of the front is what dominates, is what governs the dynamics, you can linearize. And then all nonlinearities disappear. And when the equation becomes linear, everything is easy. But when this depends on density, this depends on density, probably we have this. And I have seen papers by Maney that consider this quantity depending on the density, and then here the front suddenly has a hump or something like this, but in most cases you can perform variational analysis and calculate bounds for this velocity, upper bounds, lower bounds, but the exit velocity is not possible to calculate analytica unless you have the luck that you can solve this exactly. But
even for piecewise, would this work if d of rho had a piecewise
Yeah.
piecewise function that I could?
If you consider piecewise linear function for this, you can get exact solutions. Yes. But you have to take care also with piecewise functions,
Yeah.
because sometimes I have seen piecewise models for this bistable solution, bistable reaction, that are this. So this is linear. Here is broken, and this is linear with two slopes. This is a piecewise model for bistable, but sometimes if you compare the exact solution with this solution, sometimes it's not in agreement. So you have to be careful with this.
Any other questions? So if you are here next